Hey guys, welcome back. We're going to go ahead and finish up notes this time for this chapter 16. Last time we were interrupted by some kids making a delivery for Pi Day, and they were pretty excited about that, so that was the knocking on my door you'd heard. So we'll go ahead and pick this up. I apologize for the weird ending to the last video, but that'll give us a chance to go over this again. So the question is the solubility of silver chloride in grams per liter. Now, normally the solubility we solve for S is moles per liter, but jumping from moles to grams is pretty easy for you at this point. So we can set up silver chloride, and then knowing the charges of it, we can dissociate it into aqueous ions, silver ion, and a chloride ion. And then from our book, we can look up our KSP. So we know that much to start with. Excuse me. So initially, we have solid silver chloride before we dissolve it in anything, so we have no aqueous ions. Our change is a plus S and a plus S because there are no coefficients here. And at equilibrium, we have S for silver, S for chlorine. Now we said we don't write our silver chloride in the equilibrium expression because we don't write solids. And so here we have a 1.6 times 10 to the negative 10 is equal to S times S, so it's equal to S squared. So we say S is equal to the square root of KSP, so we take the square root of 1.6 times 10 to the negative 10, we get 1.3 times 10 to the negative 5, which means that the concentration of silver at equilibrium is 1.3 times 10 to the negative 5. Concentration of chlorine at equilibrium is the same. So how do we get to silver chloride? he's not even in this yet. Okay, so we say, well, because this is a 1-to-1 ratio, there's 1 mole of chlorine ions to 1 mole of silver ions that we have in solution. Well, where did they come from? Of course, they came from silver chloride, the solid. So if I have 1.3 times 10 to the negative 5 moles of this, it came from 1.3 times 10 to the negative 5 moles of this. It's a 1 to 1 to 1 ratio. So I can say, okay, silver chloride, its solubility was 1.3 times 10 to the negative 5 moles, AgCl, in a liter. And then I find its weight on the periodic table, and I add up the weight of silver, I add up the weight of chlorine, I get 143. So now moles cancel out, and I have grams per liter. When it's all said and done, I can say that I could dissolve about 1.9 times 10 to the negative 3, which is very, very, very small weight, grams in 1 liter of solution. So it's definitely a slightly soluble solid. Okay, so here shows you some ratios for our KSP when we have coefficients that are becoming superscripts, and then how that affects our anion and cation, and how that changes our KSP. So let's look at a different problem. We have 2 milliliters of a 0.2 molar sodium hydroxide, a strong base, added to 1 liter of 0.1 molar calcium chloride, which is a salt. Will a precipitate form or not? So what we have to do is we have to split these guys up and figure out what they can form. So sodium hydroxide splits up, becomes sodium, becomes hydroxide ions. Calcium chloride splits up, becomes calcium and chlorine. So can we precipitate a sodium chloride or a calcium hydroxide would be our question. Now you might remember from, I don't even know what chapter, forever ago, page 177 or something like that, that sodium chloride is a pretty soluble salt. So sodium chloride being very soluble is probably not going to form. It's precipitate. It'll stay dissolved in solution. Calcium hydroxide, I think, is a slightly soluble, so this is going to be the one we're going to focus on. So the only possible precipitate's calcium hydroxide for the reason I just explained about sodium chloride being very soluble. So what we have to ask ourselves is, if we solve for this as is our Q greater than our KSP? Because you'll recall, if Q is greater than KSP, we are supersaturated and will form a precipitate. If Q is less than KSP, then we will not form a precipitate because we are unsaturated. We could still put more in the solution. So we're going to go ahead and try to solve for a Q for calcium hydroxide. So if calcium comes from 0.1 mole in 0.1 liter, then its concentration is 0.1 molar. That's nice, very easy to solve for a concentration. And its concentration of the hydroxide ions comes from the 0.2 moles with 2 milliliters. So you solve for the moles and you get 4.0 times 10 to the negative 4. With the same way we did in class, 0.2 molar equals x over, what would this be? 0.002 liters, and then you solve for your concentration that way. So once we've solved for these concentrations, we can say, okay, Q is equal to my calcium concentration initially times my hydroxide concentration squared initially. And that's the subscript 0. So you say, okay, we have 0.1 times 4 times 10 to the negative 4th squared. That gives us a 1.6 times 10 to the negative 8. So we go ahead and we look up the KSP from our book for calcium hydroxide. We find that that's 8 times 10 to the negative 6. So the times 10 to the negative 8 times 10 to the negative 6 were quite a bit smaller for our Q. So since Q is such a smaller number than compared to KSP, we will not form a precipitate because the calcium hydroxide is unsaturated. We could still have more calcium hydroxide in there. So that's how you'd solve something like that. So, a little harder problem. What concentration of silver is required to precipitate only silver bromide in a solution that contains both bromine and chlorine at a concentration of 0.02 molar? So we know our bromine concentration, we know our chlorine concentration. So if we're going to precipitate silver bromide, we want this guy over here. We're going to have to build him, of course, out of silver ions and bromide ions. And the KSP for silver bromide is 7.7 times 10 to the negative 3. So we can say, of course, that our KSP is equal to the concentration of silver multiplied by the concentration of bromine. And so what we're trying to figure out is the concentration of silver. So we can rearrange this equation to solve for the concentration of silver. We have a KSP, and we have a bromide ion concentration. So our KSP is from the book, the bromide ion concentration is from the question. We find that we would need about 3.9 times 10 to the negative 11 molar concentration of silver. Now what about silver chloride? Because we don't want to get silver chloride, we only want silver bromide. So we set the same thing up with silver chloride, and we look up its KSP from our book. We set up the same thing with the concentration of our dissolved ions, and then we solve for silver. We plug the KSP in from the book, the chlorine of 0.02 from our question, and we see an 8.0 times 10 to the negative 9 molar. So we want to precipitate silver bromide, not silver chloride. And thankfully, silver bromide is a smaller number. So if we put less silver in, we get silver bromide. If we put more silver in, we get silver chloride. And so then we would say our silver concentration would need to be greater than 3.9 times 10 to the negative 11, which is the lowest amount we could have to still precipitate silver. But it would need to be less than 8.0 times 10 to the negative 9, because then we would start to precipitate silver chloride. So that's how you can answer a question like that. A little bit tougher, but it's still just manipulating our KSP equations. And then here's an example of where they added just a little bit of silver and got their silver bromide, and then added a whole bunch of silver and got their silver chloride. And they do look a little different in their colors. So the common ion effect is something that we are going to be doing in the lab, or perhaps we're already doing it. The presence of a common ion decreases the solubility of the salt. Now you'll remember this from Le Chatelier's principle, where if we're adding a common ion on the product side, then as you add to the product side, you will favor the formation of the reactant. And in dissolution work, which is what we've been doing, that reactant is normally a solid that's trying to dissolve. So we'd be making more solid. If you're making more solid, you're decreasing the solubility. So, what's the molar solubility of silver bromide? If we do this in pure water, we do this in 0.001 molar sodium bromide. So, pure water, silver bromide dissociates into silver and bromine. It's all a 1:1:1 ratio. Very easy. We look up its KSP in the book, and we have everything we need to figure out. This is a plus S and a plus S, so KSP is equal to S squared. We take the square root of 7.7. It's a done deal. There it is in moles per liter. Now, if we're dissolving it in sodium bromide, it's a little bit different. This is a salt that will ionize completely. So we can say our concentration of sodium is 0.001. Our concentration of bromine is 0.001. So if we start with the concentration of bromine at 0.001, we no longer get to do this 0, 0, plus S, plus S. We changed things a little bit. And we set up our same equation, silver bromide, forming silver ions and bromine ions. And now we say we have a lot more bromine. So our Ag plus is going to be equal to S. But our bromine, for our ice chart, the initial was 0.001 plus S. Now, if you want to use the approximation, you can, because we're assuming that because this is a slightly soluble solid, that the addition to that S is really going to be such a small number that it won't significantly change our results. And so we can say that the bromine ions are basically equal to 0.001, what we got from here, because what we got from here was 8.8 times 10 to the negative 7. So if we did add that, what you would expect to get close to that from this solid, you'd be putting in a number of like 0.001000007. Did we really change it that much? Not really, or 0.00008. You're not really changing that number much. So we can say it's close to 0.001. Now when we do our KSP, we solve for this. It's 0.001 multiplied by S, because that's bromine multiplied by silver. We're setting up the same thing we did over here. So now when we solve for S, we get that it's 7.7 times 10 to the negative 10. Now it's quite a bit smaller than this S was, which means we're dissolving quite a bit less of silver bromide than we were in pure water. And that's exactly what you'd expect with the common ion effect. If you add more bromine, you shift your equilibrium to the left to relieve the stress. That's Le Chatelier's. On the conceptual level, the difference in these molar solubilities is the difference in Le Chatelier's on a mathematical level. So hopefully that sort of makes sense. So last thing is pH insolubility. The presence of a common ion decreases solubility. That's what we just talked about. And the insoluble bases will dissolve in acidic solutions. Insoluble acids dissolve in basic solutions. These are largely for the same reasons that we just talked about. It kind of comes down to Le Chatelier's principle. I'll give you an example. Here's magnesium hydroxide. It's our base. It dissociates into one magnesium, 2 hydroxide ions. Very easy, something you've seen before. Our KSP is our products. We square the hydroxide, something you've seen before. 1.2 times 10 to the negative 11th. Here we can solve for KSP, saying S is what's coming from magnesium, and 2S is what's coming from hydroxides, and then we have to square that concentration. So we end up with 4S cubed. And so if we set our 4S cubed, which is our change in solubility, to our KSP, we can solve for S. We just take 1.2 times 10 to the negative 11, we divide it by 4, we raise it to the power of 1/3, and we've got an S of 1.4 times 10 to the negative 4th molar. And so if that's our concentration, then we know our hydroxide ions, because our hydroxide ions are 2S. So there's twice as many as just S would be on its own, which this is S. So we just take 2 times that, and we get 2.8 times 10 to the negative 4th molar. We have a hydroxide ion concentration. From that we can solve pH, we can solve for pOH, very straightforward stuff. So, if we change our pH concentration, if our pH is very low, then we lower our hydroxide concentrations. And if we lower our hydroxide concentrations, then our hydroxide will of course be reacting with hydrogens to make water. And so as we start to remove the OH, we are going to favor the formation of more aqueous product. So the more acidic we get, the more we react with the hydroxide ions. Hopefully that makes sense. Acid, this guy, reacts with this guy. As he takes this away, we relieve stress on the right side, and so we make more product from that. So if we increase the solubility of magnesium hydroxide, if we were to dissolve this in an acid as opposed to dissolving it in water. So at a pH greater than 10.5, we're becoming very, very basic. You become very, very basic. You have a very, very high hydroxide concentration. So of course, Le Chatelier's principle again, if you're adding all this hydroxide, you're going to push that equilibrium to the left, and you're not going to be able to dissolve as much. You will decrease the solubility of that solid. So, complex ion equilibria and solubility. A complex ion is an ion that contains a central metal, cation, and it's bonded to one or more molecules or ions. So here's cobalt chloride, it's a complex ion. And we use a Kf for these guys. This is called the formation constant. Some people call it the stability constant. It's the equilibrium constant for that complex ion formation. And just like all the other equilibriums we've done, it's product or products divided by reactants. So if you increase the Kf, that means the complex you form is very stable. Hopefully that makes sense. If our Kf is high, we have a lot of product, and the only way for our product to have a high concentration would mean that we're making something that's stable. If it's unstable, it would rapidly dissociate into its component parts, and if it dissociated into these, we'd have more reactants, and our Kf would be a lot smaller. So here is your cobalt, let's see, cobalt 6 hexahydrate. Sound good to you? Sounds good to me. I hope it's right. Cobalt hexahydrate, being purple, and then if you add an acid to it, it becomes cobalt chloride, and it becomes blue. So that's kind of cool. So how does this change solubility? Well, here we have a silver nitrate and a salt, and if we can form a complex ion, we can actually change what's dissolving in this. So we add ammonia, and we end up getting silver ammonia 2+ ion, and we are forming this complex ion and changing completely what's going on in this test tube. So here's an example of the table from your book, which is the complex ion, how you form it, and what its Kf is. And this one's a little tricky. This is precipitating different ions out. If you start with hydrochloric acid, you can precipitate out these ions. And then if you add acidic solutions to H2S, you can precipitate out these. In basic solutions, you can precipitate out these. And no precipitating reagents are down here. And so it just shows you the different solutions you can use to get a different product, which is kind of cool. So qualitative analysis of cations. You start with the solution that has all of these ions and cations. You add hydrochloric acid, and you get these groups out. Silver chlorides, mercury chlorides, lead chlorides. So we've got some left over. So now we add dihydrogen sulfide. We filter it out. Now we get our group 2s, our copper sulfates, cadmium sulfates, mercury sulfates, all of our sulfates. Or, sorry, sulfides. It's not SO4. It's not sulfate. It's a sulfide. My mistake. So you've still got some stuff left. More ions, more remaining groups. We had sodium carbonate. Now we get our group 4s, our carbonates, barium carbonate, calcium carbonate, strontium carbonate. And what's left is sodium, potassium, and ammonium ions. So kind of cool. We can add these different things. This is something you've done before. If you want to know what cations are left, you can do a flame test. You guys also know that it's oftentimes not quite as picture perfect clear as it is in a textbook, but there you have it. Copper glows green, potassium, kind of this blue-purple, sodium a bright yellow, and lithium the red. So a flame test is one way you can tell what metal ions are left in your solution and if your precipitation and reaction was effective or not. So last thing is your chemistry reaction, how an eggshell is formed. Calcium carbonate makes calcium carbonate, which is great. Here shows you water and carbon dioxide with this enzyme carbonic anhydrase forming H2CO3, H2CO3 in equilibrium, a weak acid, weak base equilibrium, and then its conjugate base in its weak acid, weak base equilibrium. And that's what gets us this carbonate that we later use to build the eggshell with calcium. So there you have it, an electron micrograph of eggshells.